Okay. All right. Did you enjoy your blizzard day off? Me too. We missed one lecture on material properties, but I think we'll be fine. We'll just go a little faster, or probably other places we won't be able to go as slow as we used to, but we'll just move forward from there. I want to remind you where we are. We've been talking about material functions, and we're more or less done. So let me just review what we've done, what we've been doing. We've been talking about various material functions in shear and elongation. And this is, for instance, the small amplitude oscillatory shear material function. And all of our material function slides look like this. They have a kinematics section and a material function section. So when I say the kinematics that go with a material function, I mean pick the flow. This is shear flow. It has one parameter in it, which is sigma dot. And so in the case of small amplitude oscillatory shear, sigma dot is given by the cosine function. And this parameter function may have in itself other parameters in it. For instance, gamma dot naught is the magnitude of the shear rate, and omega is the frequency. Now, when we impose these kinematics, kine from the Greek meaning motion, okay, when we apply this motion, we get a certain stress response. And then from the stress response, we define the material functions. And the material functions are, in this case, G prime and G double prime. So we went through this last time, and we talked about how to produce the flow and about how the stress response, if we assume that the stress response is a stress wave in phase with the shear rate or the strain, either one, excuse me, not in phase, but with the same frequency as the shear rate or the strain, then we could, if we assume that it produces such a stress wave, but out of phase, we could break that into two parts, a portion that's proportional to the sine omega t, and a portion that's proportional to cosine omega t. In other words, a portion in phase with the strain is a sine wave, or a portion in phase with the rate is a cosine wave. Going back to my kinematic slide, here's my shear rate, it's a cosine wave. And we get the strain wave by just integrating that between the limits of 0 and t, and we get that strain is a sine wave. So this is a very useful material function because it allows us to do viscoelastic properties, because the portion that's in phase with the strain is acting like an elastic solid. It's the elastic response of the material. And the proportion in phase with the rate is like the viscous response. Viscosity is proportional to rate of deformation, and strain is proportional to, stress is proportional to strain for an elastic solid. Then we also talked about, finally, our elongational material functions. Again, kinematics and material function. So really don't hesitate when you're asked a question to predict a material function. No hesitation. Start immediately by writing down the kinematics, because that has to be the starting point. The constitutive equations that you have are a function of the velocity vector, and there's the velocity vector. So you can always just plug in the velocity vector to the constitutive equation, predict stresses. The stresses go into the definitions of the material functions. In the case of elongation, they're these Eta bars. We did the prediction for a Newtonian model, and I think I have those slides here. Let me remind you what they look like. No, that's shear flow, not yet. This is what we did last time. What is the elongational viscosity for a Newtonian fluid? We started with the kinematics. So those are the kinematics of elongational flow. If we know V, and we're trying to calculate a stress, the constitutive equation works for any V that we would know. Once we specify the V, we plug it in here. So we need del V. So that's what we did. We calculated del V from this V. Del V transpose is just the transpose of that vector. So here was del V. It has diagonal components. Del V plus del V transpose is the same thing with its transpose added to itself, so it just doubles it in this case. Calculating the stress is multiplying by minus mu. And then we go to the definitions of the material functions. Tau 33 minus tau 11 over gamma dot naught is eta bar. Calculate that out and we get the Troughton viscosity. So as you see in the homework also, it's the same drill. Start with the kinematics, plug them in the constitutive equation. The constitutive equations get more and more complicated, but it's the same idea. So at least if you're puzzling, it should be over the details of the constitutive equation, not over how to start. How to start should always be, I know the velocity field. When I'm predicting a material function, I always know the velocity field. And since the constitutive equations will always have velocities in them somewhere, plug them in to where you see velocity and then worry. You'll see that as our constitutive equations get more complicated, there'll be something to worry about in terms of making that calculation, but that's always the way it starts. You're always predicting a stress. Okay, so we did that. And then we looked at some data for elongational viscosity and said that this Newtonian prediction comes out to be true, that when you put a Newtonian fluid into an elongational velocity profile, you do calculate a stress that calculates out to have a viscosity 3 times the shear viscosity. And then we started on this. I'm trying to remember how far we got on this. We started on this problem, which is how to calculate Eta bar, the steady elongational material function, for our little FACO constitutive equation. And this leads to a contradiction, and that leads us on to the next part of the course. So we did this. What is Eta bar for a fluid that follows this FACO constitutive equation? This was the constitutive equation that when you plot this function m as a function of shear rate, we wanted to make it look like the viscosity function that we measure for real polymers. And there's some critical shear rate beyond which we see shear thinning, and below which we see a constant value. So we made up this function where it goes to the plateau m at low shear rates, but at high shear rates it becomes this shear thinning power law type model. So what is Eta bar? We're predicting a material function. That means we always start with the velocity field. The velocity field goes into del V transpose. It's the same del V transpose for the Newtonian case because it's calculated straight from the velocity field. So we skipped right to that step. Calculating del V and del V transpose, we get gamma dot. But then we plug gamma dot into our constitutive equation. So we have to multiply by minus this function of gamma dot naught. So we multiplied that by minus the function, and that gives us the stress. Now, we've calculated, I know at this point I rushed to the conclusion, so I'll slow down and do that conclusion again. Again, it's the same pattern when calculating a material function. We've calculated the stress. Let me write it out neatly now. The stress is equal to minus this function, which is m of gamma dot naught, times this tensor, minus epsilon dot naught, 0, 0, 0 minus epsilon dot naught, 0, 0, 0, 2 epsilon dot naught. So that means that, and then let me write what this function is on this same piece of paper, where m is as we wrote before, m of gamma dot naught is equal to the constant m naught, let's call it, for gamma dot naught less than the critical. And it's equal to this power law model when gamma dot naught is greater or equal to this. So it's a little bit tricky because it's this discontinuous function. If I just wrote, sine of gamma dot naught in the front, you would just multiply the sine through and you would know what you were doing. And it's really no different here, except that we have to talk about this functional form is a discontinuous function, so it's a little tricky. But we want to then go to the definitions of the material functions. Eta bar is tau 3 minus tau 1 over epsilon dot naught, the whole thing negative. So we need tau 3. Tau 3 is this element. Don't forget it's multiplied. So it's minus the function m of gamma dot naught times 2 epsilon dot naught. And tau 1 is minus m the function gamma dot naught times minus epsilon dot naught. And so our eta bar is minus tau 3 minus tau 1 all over epsilon dot naught. So we get our 3 again. This is minus 2m minus 1m, so we get minus 3. And a minus side in front means we get 3 epsilon dot naught times the function m divided by epsilon dot naught. So we get 3. Everything seems to be going very well. The only problem is we have actually a problem if we try to sketch this or even understand what we've just predicted. This function says 3 times our m function, which is m naught, when the shear rate, we're not even shearing, okay? When the shear rate is less than gamma dot critical, it's equal to little m gamma dot naught. We don't even have a gamma dot naught. This flow has got an epsilon dot naught. So it's kind of a confusing thing. I mean, this is the kind of conundrum or dilemma I know that to you probably think, oh, I just don't get it. It's probably epsilon dot naught. I'll just substitute epsilon dot naught. That's probably the answer. But the truth is that it's not the answer. It's a stupidity. We made up this constitutive equation by saying that in shear flow, we knew what the viscosity prediction was. It looks something like this. But now we're not in shear flow. And how would this shear flow impact elongation of flow? I mean, it's not even, there's really just no way to say. So this is a dilemma. I mean, there is no gamma dot naught in this flow. So should we change gamma dot naught to epsilon dot naught? Should we change gamma dot naught to 3 times epsilon dot naught? To some other parameter, the square root of epsilon? No, that wouldn't be the right units. It's weird, okay? We have to examine this problem. And this brings up an important point about these kinds of models. the models, the constitutive models themselves, cannot have parameters in them that restrict the models to one flow or another. This parameter, gamma dot naught, restricts this model to shear flow. Our little FACO model has been restricted to shear flow. We don't want it to contain such a parameter. If we make up constitutive equations, tau equals some interesting function, right? It's going to have v's in it somewhere. So maybe del v transpose, maybe some time integrals, maybe some other interesting things. It cannot have v2, v1 in it, for instance, because that refers to a specific flow. It cannot have gamma dot naught in it because that refers to shear flow. It cannot have epsilon dot naught in it. That's a parameter of elongational flow. It can have parameters in it, but they cannot be, it cannot contain flow-specific parameters. It just doesn't make sense. This is good. Constitutive equations are good for all flows. And so they cannot contain parameters that are specific to one flow. And this is where the invariants become useful to us, okay? Because we can, instead of putting parameters, we need some kinematic parameters. We need some way of saying that the rate of the flow, the rate at which the flow goes, changes the response of the material. Because we see it in shear, and we suspect we'll see it in elongation. So we need some parameter that comes from that kinematic part of the equation. We can't say gamma dot, and we can't say epsilon dot, but we can say something, some kind of a kinematic parameter that's invariant, for instance, okay? What kinematic parameter should we use? Well, we can do things like we can use the magnitude of the velocity. The magnitude of the velocity we could calculate for any flow. We could do something like the magnitude of the rate of deformation tensor, or one of the other invariants of the rate of deformation tensor. We can do all kinds of kinematic parameters that are neutral to the flow that can be calculated for any flow, okay? Invariants, such as magnitude. These are magnitudes of a vector, magnitude of a tensor, can be used as kinematic parameters. Okay, so let me see if I've made any sense. Let's see what the magnitude of the rate of deformation tensor is in shear and elongation, and see if that looks like a useful parameter to us. So let's get specific. We have two flows. We have shear and we have elongation. For now, let's talk about uniaxial. We can also deal with the other two as well. For both of these flows, we know what the rate of deformation tensor is. So let's do steady flow. We've calculated these before, and you may not remember, but you'll recognize them in your notes. This is the rate of deformation tensor for steady shear flow. And this is the rate of deformation tensor for steady elongational flow. It was minus epsilon dot naught, minus epsilon dot naught, 2 epsilon dot naught. Now, before, when we made up that constitutive equation, we used the parameter that came out of the velocity. And we just had a problem because we made up the function in shear and we weren't able to translate to elongation. What if we use the magnitude of the tensor and we go back and look up what that was? So we go back to our notes, or we go back to the book, and we find that the magnitude of a tensor is the tensor double dotted with itself over 2 quantity square root. Okay, so we're going to use all that math that we spent our time on, this vector and tensor math business. So now we need to take the double dot of a tensor. So Einstein to the rescue. Gamma dot 2, 1, E2, E1. Excuse me, what am I doing? Gamma dot ij, EI, EJ, double dot. Gamma dot pk, always starting over with new letters, EP, EK. And the double dot was to dot the 2 nearest, so that's delta JP. And the 2 farthest, that's delta IK. It's not quite equal. So I've got gamma dot I becomes K, J becomes P, gamma dot PK. No unit vectors left over because this is this scalar product of 2 tensors. It leads a scalar result. It's going to give us a number. The magnitude is going to be this number divided by 2 square root. So what does this say? It says multiply gamma dot kp times pk. So 1, 1 times 1, 1. 1, 2 times 2, 1. 1, 3 times 3, 1. 2, 1 times 1, 2. 2, 2 times 2, 2. 2, 3 times 3, 2. 3, 1 times 1, 3. 3, 2 times 2, 3. 3, 3 times 3, 3. So the only time we didn't get 0 was 1, 2 times 2, 1 and 2, 1 times 2, 2. And it happened twice. So we get 2 gamma dot 1, 2 times gamma dot 2, 1. And they're equal to each other, divided by 2 quantity square root. So gamma dot in shear is equal to the square root of gamma dot naught squared, so it's equal to gamma dot naught, absolute value. It can be positive or negative, but when we take the square root, the definition of magnitude is to give a positive number, so it's absolute value. We can do the same for elongation, okay? Gamma dot elongation okay, we've got to go back and look at that tensor. It's going to be the square of this term, this times that times that times that, the square of this term, that times that times that times that, the square of this term. So it's the square of this plus the square of this plus the square of this. You got that? Does that make sense? I'm just multiplying across the diagonal. 1, 1 times 1, 1. 1, 2, 2, 1. Just the mirror image across the diagonal, but you have to make sure you pick up every pair. Okay? So it's the square of the first, the square of the second, the square of the third, all divided by 2 quantity square root. So that's 6. 6 over 2 is 3. So I get the square root of 3 epsilon dot naught, or I get epsilon dot naught square root of 3 plus. This also has to be absolute value. This magnitude of this tensor is defined as gamma dot with no subscripts on it. And this is invariant. Okay, this is a shear. This is a invariant quantity. Invariant to change of coordinate system. And it's something, that doesn't mean these two numbers are equal to each other because these are for two different flows. But within each flow, it doesn't matter what coordinate system I expressed it in, this is going to be the number. So that's an important aspect. But in addition, it's something I can calculate for any flow. It is a kinematic parameter I can calculate for any flow. So if I made up constitutive equation and I wrote it in terms of this, the magnitude of the gamma dot tensor, then when I switch to elongational flow, I can figure out how to write it in terms of the parameters of that flow. When you write the model that we made up this way, you get a legitimate constitutive equation that's correct. Okay? We'll talk about that more completely when we introduce the power law model, which is similar to our made-up flow. So I'll summarize this discussion by saying we can make up a better constitutive equation by using gamma dot instead of gamma dot naught. This is a shear property, and this is a property that can be calculated in any flow. And gamma dot is equal to gamma dot naught in shear. So we'll be able to use it for shear thinning, and it's equal to epsilon dot naught root 3 in uniaxial elongation. So this is summarized somewhat on my lecture slides. Here's our FACO model. It has this illegal shear parameter in it. And here's what I said. The model contains parameters that are specific to a particular flow. It's impossible to adapt it to elongational or other interesting mixed flows. It should only contain quantities that are independent of coordinate system in addition, frame invariant. So we can salvage the model by replacing that flow-specific parameter, which is something that is frame invariant and not flow-specific. And that's what we just talked about. If we change m to be a function of the magnitude of the rate of deformation tensor, then in shear flow, this magnitude will be the same thing that we hoped for. It's going to be equal to the shear rate. And so this will still look like that same model that matches flow behavior. In elongation, we don't know how good it will be, but at least it won't have the problem we've surfaced. So we'll come back to this later. All right, so we could keep going and do more examples of elongational stress growth, elongational stress cessation, elongational creep, but the plan is always the same. The kinematics are defined, the material functions are defined, and we can predict them using constitutive equations. There's even small amplitude oscillatory elongation. When you put a sample between parallel plates and just compress them a little bit along a sinusoid, that's small amplitude oscillatory elongation. And in fact, it gives the same, because it's in this linear strain limit, it actually gives the same thing as small amplitude oscillatory shear. It doesn't matter that it's elongation. Everything is just 3 times. Okay, that's because of some of the definitions, but they are very easily interrelated. And the details of that are in the book where those material functions are defined. Stress growth in elongation looks a little bit like this. In low rates, you get a very nice envelope here at the bottom. This is the elongation at low rates. At high rates, though, the stress comes up and then takes off, and eventually the sample breaks. So at the tip of each of these curves, the sample is breaking, and it's never coming to a nice steady plateau. Remember, in shear, it went up and plateaued to a steady shear value. In elongation, it comes up and plateaus to a steady shear value only at very low rates. At higher rates, it comes up and breaks. There are some models that exist. These are constitutive equations. One's called the pom-pom model that predicts that the sample should come up, straighten, harden, and then come to a steady state. That's never been observed, but there are models that predict that that's the way it should happen. This is data on low-density polyethylene, and this is data on polypropylene. Okay, so we've finished chapter 5. And I think it's a good time to take a little stock of where we are and figure out what we've learned so far. So what we've been talking about so far, we did some math. I think that was chapter 2. And you see we've used it. Okay, this is just-in-time learning. All that stuff we learned about vectors and tensors, it keeps coming back. The invariants are coming back. The Einstein notation is coming back because fundamentally the language of rheology involves those vectors and tensors. We studied Newtonian fluids. Newtonian fluids are kind of a 0th order for us. It's a baseline for us to figure out how this system is working. And the main output of the Newtonian fluids was a method of calculating flow problems and also our first constitutive equation, the Newtonian constitutive equation. We just finished a chapter on material functions. And what were those about? The material functions were protocols for non-Newtonian behavior. Protocols means something like ASTM. They're standardized tests that we're using as a way of agreeing on how to describe non-Newtonian behavior. So material functions are things like shear viscosity, first normal stress coefficient second, or elongational viscosity, or in small amplitude oscillatory shear, G prime and G double prime. And material functions always have kinematics and then definitions. And now we're going to move on to experimental data. Oh, I missed one chapter. 4 and 5, material functions and standard flows. These were together, really. And then 6, experimental data. Now, this standard flows and material functions comes out like a little bit of vocabulary. This will be how we discuss material behavior, and now we're going to discuss material behavior. And this is how rheologists discuss things. They say, well, what's the viscosity of the material? How does it behave in steady shear? What's its elongational viscosity? What's its G prime and G double prime? How does it behave in small amplitude oscillatory shear? Does it show an overshoot on startup? how does that change with molecular weight? How does viscosity, how does G prime and G double prime change with molecular weight? How do they vary with temperature? How do they vary with pressure? That's the next part of our discussion. Once we've got a little bit of more understanding using this vocabulary, we can move on to new constitutive equations, and that's chapter 7. Newtonian fluid, generalized Newtonian fluid, constitutive equation. Chapter 8 is the generalized linear viscoelastic constitutive equation. Chapter 9 is advanced constitutive equations. So in chapters 7, 8, and 9, we're going to be trying to model fluid behavior. So before we can model the fluid behavior, we have to know how materials behave. And so this is what makes rheology so front-end loaded. We had to learn all these things, and we're all probably thinking, where are we going with this? You know, where are we heading with this? And I'm trying to give you an idea where we're heading. We're going to try to model fluid behavior, but first we have to talk about fluid behavior. So we're almost there. We've got the math background we need. We understand constitutive equations. We've got the background in vocabulary of standard flows and material functions that we need. Now we have one last piece, and if we can just hang on, we're going to learn how materials behave, so that when we look at constitutive equations, we can say this is a good one because it actually describes how materials behave, or this is a bad one because it doesn't actually describe how fluids behave. But until you know how fluids behave, you can't even agree with me. You would just have to take my word for it. Oh yeah, she says it's a good one. She says that's a bad one. I believe her because she's going to ask me that later. But instead of that, we'll first get you up to speed so that you know how materials behave, so that you can see why the materials, why the changes we're making from one generation of constitutive equation to the next is actually making them better. Or in some cases, what we'll see is it makes some things better, it makes other things worse. And that's unfortunately the state of the art in rheology, is that every improvement you make makes one thing better and something else worse. We're not able, most of the time, to find the perfect constitutive equation. So that means we have to remember all of them, not necessarily memorize, but remember what their strengths are, so that when we do actual modeling and calculations, we use the right one. We use a constitutive equation that performs well in this particular manner. So, chapter 6. Chapter 6 is going to be on a whole bunch of data. And everybody asks every year, well, you know, how much of this am I supposed to know? And what we're going to do as we go through chapter 6 is we're going to jot down how much of this are you supposed to know? Because you know I do give closed book tests. So that means you're not going to be able to page through the book to find the answers when I ask you things. So what I'm going to do is, on a sheet of paper here, we're going to summarize as we go along. I'm going to describe a lot of things, but I'm going to summarize the things that I really think you should take away as the take-home message from this discussion. So this is the outline of what we're going to cover. We're going to talk about steady shear flow, and the materials I'm going to discuss are polymers. This is a polymer rheology class. We could hope to discuss even more complicated things than just simple polymers, but you'll see this is complicated enough for a first step. I'll talk about these topics, measurability issues, variations that go with polymers, such as variations with molecular weight distribution, and architecture. And then I'll talk about temperature and pressure a little bit. And this I'm going to spend most of my time on, steady shear flow, because it's the thing we know the most thing about. Then later, we're going to go to unsteady flows, elongational flows, etc. So we'll move on through the program. Okay? So how do materials behave? If you put polymers into a shear cell and put that velocity field on them, the one that goes with steady shear viscosity functions, this is how they behave. Now, you've seen this slide before, and let's look at it more closely. It is a slide that says that the viscosity varies with shear rate. And now I'll point out a subtlety of this graph. Notice how this is labeled. It's not labeled gamma dot naught. And that's because of what we just discussed. It's labeled in terms of the magnitude of the rate of deformation tensor. It's always positive. Even though when you shear, actually, this flow has, let's say, in my chosen coordinate system, this flow has a positive shear rate. But if I turned it the other way, there would be a negative shear rate. But there's no real fundamental difference between these two flows. I just went left or I went right. And the magnitude of the rate of deformation in both cases can be the same if I move the plate with the same velocity. And so that's why these will always be reported in terms of gamma dot, the magnitude of the rate of deformation tensor. So it's not a constant, which says it's a non-Newtonian fluid. And we define a couple of things about these curves when we talk about them. One is that there's a zero shear plateau, it's called. These are lower and lower shear rates. And so at the limit, as the shear rate gets lower, it hits a plateau very often, and that's called eta naught. First normal stress coefficients have the same shape, but they're not, it's just the same general shape. They're actually not congruent. The slope, the thinning nature of psi 1 is much greater, usually greater than the thinning nature of viscosity, but they both do approach a plateau. So where's our experimental data summary, page 1. I'd like you to please remember that in steady shear of linear polymers, if we plot on a log-log graph, these are log graphs versus gamma dot, viscosity goes from having a plateau to thinning, usually, and psi 1 goes from a plateau to a steeper thinning. And these two plateau levels are called eta naught and psi 1 naught. This one is called the zero shear viscosity. This one is called the zero shear first normal stress coefficient. Now, I've actually only shown you one set of data, so let's look at some more. These data were from a concentrated solution of polybutadiene. Here are some more concentrated solutions of polybutadiene. And these have been taken on samples that have a variety of different molecular weights. Okay? Now, why don't you tell me, what do you see when you look at this data? So this is viscosity up here. This is first normal stress coefficient on a different axis. So look, this has been shifted downward by 3 decades. So in fact, some of this data is the data from here. This one was 170. So wait, which data is that? Page 170, excuse me. So this data, well, let's just see. It has a zero shear viscosity of 2 times 10 to the minus 4. So it must be this pink curve. There's 2 times 10 to the minus 4. So that data is right here. And so its first normal stress coefficient is right here. And you know they intersect. So this one's been shifted down by 3 decades. So tell me in words, what do you see is the effect of molecular weight on viscosity?
It increases that?
It increases. So at every shear rate? What do you see?
The plateau.
The plateau, the zero shear viscosity increases with molecular weight. By a little or by a lot? It's on a log scale. Does it double? Does it triple? Does it go up by an order of magnitude? What does doubling look like on a log scale? If it starts out as 1, becomes 2. Okay? So doubling, which in our mind, that sounds like a lot, right? If the viscosity doubles, that sounds like a lot. Doubling of viscosity would be, for instance, here, between 350, if we double 350, we get 700, right? And this one's 800. So the red is more than double the molecular weight of the pink. So the red, is that double the viscosity? 15 times the viscosity, exactly. So doubling it would be like up here somewhere, like hardly anything. So it's an enormous change in viscosity when you double the molecular weight. But as I was trying to make you see, what happens at high shear rate? Nothing. Nothing. Okay? The viscosities are all the same at high shear rate. Okay, this is complicated. This is interesting and complicated. So when people say the viscosity is a function of molecular weight, a very strong function of molecular weight, that's only true at low shear rates. And it is true. But at high shear rates, doesn't make difference. Doesn't make a bit of difference. What about first normal stress coefficient? Would you answer a question, is first normal stress coefficient a strong function of molecular weight? How would you answer that? Yes, but only at low rates, right? Here it's happening again. And in fact, it's even more dramatic, I would say. So if somebody asked me, which is more dramatic, the change in viscosity or the change in first normal stress coefficient, looking at this, I'd say it's the difference in first normal stress coefficient. It's a much higher number of decades of difference. But it's having the same congruence down here at high rates. Now, in most introductory polymer classes, they only talk about the zero shear viscosity. And maybe you've seen, let's see if I've got it here. There. Maybe you've seen this plot before. If you've taken an intro polymer class, you've probably seen exactly this plot before. Now that you know something about rheology, let's look at this plot. What do you see? What does it mean that it has this little 0 on it? It's that zero shear viscosity. Okay? This is a plot of zero shear viscosity, that plateau, as a function of molecular weight. And so if you just plot that plateau as a function of molecular weight, it goes to the 3.4 power. So when you double the molecular weight, you have 2 to the 3.4 times as high viscosity, which is 10. Doubling it is a factor of 10. Okay? This only happens above some critical molecular weight. Below that critical molecular weight, the slope is 2. Very interesting. But no matter what you slice, these are all zero shear viscosities. It only is telling us the difference in the viscosity at low shear rate. So there's something to summarize there on our experimental data summary. We're still under steady shear of linear polymers. So let's call this A. Part A, we want to know the general idea, that there's mostly shear thinning and that first normal stress difference is thin. Page 2, B, molecular weight effect. two things that we noted. That both viscosity and first normal stress coefficient, as a function of shear rate, had a strong effect, but the effect went away at large rates. So there's a big effect on eta naught and a negligible effect on eta as gamma dot large, high shear rates. And the same is true for first normal stress coefficient. And the second is this famous curve, but I'll put that up again because I'm out of time here. So you see how this is moving along. We're going to talk about it, and then we're going to summarize the things that I want you to be able to tell me in the future. Okay, and I'll continue with that on Wednesday, and I'll have your homeworks graded by Wednesday as well.